I'm just going to lay out a disclaimer that I'm purposely taking a stubbornly information-based perspective when I'm going to talk about invariants and symmetries and equivariants that exist in the macro state and also that exist in the quantum state. I'm just thinking of them very specifically as information that is preserved in the physical state space, whether it's large scale or small scale. And what we're exploring is the phenomena that factors from non-quantum macro states like global states. These can, in some cases, provide invariant structure that quantum states obey. And they can be observed in large collections of particles like condensed matter, in topology insulators, and in magnetic compression of electrons, like the Hall effect, to name just a few. Now think of the sun's surface. There, magnetic fields are tangling and they're knotting up in similar symmetry-driven ways. The plasma follows field lines that twist and they reconnect, and a visible macro-scale cousin of the abstract twist at the U and the SU in those transformations. And this is nature showing us topology in action. You can just look at the sun. Well, you can't look at it. I mean, you have to have filters, but you can see that topological behavior happening on the surface of the sun. But in topological insulators, a related invariant, often a Z sub 2 analog of the Chern number, guarantees the presence of surface edge states, a generalized Hall-like topological projection without requiring an external magnetic field. The bulk electrons in the core, they provide the structure that the free electron flow in the surface has to conform to, and this creates a persistence in the quantum states of the surface electrons. In quantum Hall effects, the quantum states are not easily exploited, but topological insulators expose quantum effects to persistence and they allow manipulation. Now let's consider the macro state where you have special orthogonal, special Euclidean symmetries. Like in data science, these types of symmetries are useful for single value decomposition of principal component analysis, and they facilitate data compression in complex data. So your special orthogonal and your special Euclidean are families related to macro states, while your unitary and special unitary are related more to quantum states. However, we can see in both of these classes of or scales of invariant, we can see both a utility for data processing and for information technology. Special orthogonal shows up in PC and SVD, as we mentioned, where orthogonal transforms preserve the inner products, making them perfect for rotation in feature space. And unitary transforms, like the U and the SU, these are the quantum analog in the complex domain, where they preserve probability-like norms instead of simple Euclidean ones. So thinking of SO and SES coarse level spatial symmetries and U and SU as fine level quantum symmetries is an intuitive way of mapping between data science and physics. So, is it fair to say that at a conceptual level, Chern-Simons phenomena can be laid alongside coarse global topological structures like SO and SE in classical symmetry by analogy, and that global structures sometimes inform what finer quantum-like transforms like the U and the SU transforms do or do not do? I think it is fair to say that. But technically, of course, Chern-Simons itself is rooted in the quantum gauge world. It's not a separate classical symmetry group, and we're not looking for a direct literal mapping, but what we would like to find is a translation bridge in information terms between the coarse-grained and the local microstates through the Chern-Simons analog. I'd like to find that. Well, here's the point, though, that the Chern-Simons theory in standard use lives, of course, like we said, in the quantum gauge field domain. Again, it's not a separate macro-level language, but observation points to a holistic coupling, maybe. That invariants at the macro scale, these global topological structures, and invariants at the micro scale, which would be quantum symmetries, they clearly do overlap in their persistence. So the persistence of information between the two scales does exist. In reality, certain large-scale constraints, like global magnetic topology, for example, these do constrain the possible local quantum configurations. And stable quantum structures can, in turn, imprint onto the macroscopic state. So, while the textbooks keep these in separate silos, I think nature does not always do so. I think it's obvious that nature doesn't always keep them separate, right? Stability in one scale can reflect and reinforce stability in the other scale through shared symmetries and through topological invariants. Persistent information that can cross scales through a bridge. Now, putting aside the classical textbooks and standard literature, standard use, I think it's empirically true that there are invariants in both the quantum states and the macro states, and that these invariants can be formally described as persistent information. I think that's true. So it should follow without argument, then, that persistent information is a commonality between the quantum and macro states. And classically in the literature, we may have been overlooking some kind of reliable connective tissue here between the two scales. And if we think purely in terms of information that doesn't get scrambled under allowed transformations of a system, then maybe we can make the following claims. Okay. The first claim is that in quantum states, persistence does show up as topological invariance. You see it with Chern numbers, with Z2 invariance, with Z sub 2 with winding numbers, etc., etc. There's more. And that these quantum persistent invariants, they do survive under local perturbations. They're encoded in the shape of the wave function space, and they're preserved by the quantum symmetries, the unitary and the special unitary and others. So that's the first claim. The second claim is that in the macro states, persistence appears in large-scale geometric or topological features like magnetic linkage, like knotting in plasma loops, or even think crystallographic order in solids, or symmetries in a macro flow field. These large-scale topological or geometric features, they can constrain possible micro-configurations. And they're often described by other symmetry groups like SO or SE or etc. But the concept of an invariant is the same. It's a descriptor of state unaffected by allowable changes. So let's talk about this bridge. The Chern-Simons theory, again, lives natively in the quantum gauge field world, but the underlying mathematical notation of a topological invariant that's defined via a connection like a gauge field over a manifold. This underlying mathematical notation, it doesn't really demand a scale, does it? Nature can realize such invariants in macro domains, plasma topology on the sun again, and in microdomains like Barry curvature and the quantum Hall effect. So with these two scales, when they are physically coupled, like in a magnetic solid whose bulk field topology constrains electron surface states, or when they're coupled in an astrophysical plasmas where field topology channels particle motion. In those cases, the persistence at one scale becomes a shared persistence across scales. We see it in nature. And that's when the silo collapses. That same kind of conserved information is expressed in different degrees of freedom, but it's described by related mathematics. Now, looking at the intersection between matter and energy could help us better define the information persistence across states. For example, consider the conversation between matter and energy in stellar manufacturing or in neutron bombardment, where one process converts energy into matter and the other process converts matter into energy. I'm saying that the world of the macro and the world of the quantum are in very close proximity in those processes, and information relation may reveal itself here. We're essentially arguing that information persistence, the survival of certain invariant structures under allowed transformations, this is a scale agnostic principle. It doesn't matter which scale it is, the principle remains the same. I think we can't argue that. So let's think about stellar fusion. Think about neutron capture. Think about any other similarly high energy process. Matter and energy conversion sits at the boundary where macro scale fields and flows, like pressure, like magnetic topology, they directly interact with the microscale quantum states, like nuclear binding, like particle symmetries. So here, invariants are not just abstract. They can be, number one, macro constraints, again, field topology, angular momentum conservation, or they could be, number two, micro constraints, which would, like quantum numbers, like gauge invariants. So because the system couples strongly across scales, persistence can appear in both domains simultaneously. For example, a knot in a magnetic field, that's macro topology, it might preserve phase relationships in particle motion, and also conserved quantum numbers can determine macro reaction pathways. So you've got this interplay between the two scales through a bridge. So just to say it succinctly, in these high energy contexts anyway, macro and quantum symmetries aren't separate silos. They are parts of a single constraint web. Information persists across matter and energy boundaries, and it's like a unifying feature. And the mathematical machinery, when you're looking at like topological invariants, symmetry groups, this machinery can describe across the scales. So in this argument, we're kind of pushing beyond the textbook framing. The idea that topological invariants can exist at both macro and micro domains is obviously correct. And mathematically, topology doesn't care about scale, does it? No. So physically, there are real systems like solar plasma, topological insulators, Hall systems, nuclear fusion environments. You could start listing many, couldn't we? There are these systems that, where large-scale field topology constrains local quantum states and where quantum invariants feed back into macro behavior. And the information persistence framing is a valid framing. Invariants are conserved descriptors of the state, and this is scale agnostic. The coupling across the scales is, I think, under-acknowledged in standard treatments, which tend to silo macroclassical fields and silo the micro-quantum fields, because nature doesn't silo them. So a new perspective might be gained here with this viewpoint. We're proposing a unified language of persistence that treats macrosymmetries, for example, SO and SE, and quantum symmetries, for example, SU, U, Chern invariants, we're treating them as different expressions of the same underlying idea, information that resists scrambling under allowed transformations. So what this does then is it's reframing Chern-Simons not as purely quantum, but as part of a continuum of topological invariants that manifest wherever field-state coupling is strong enough to bridge the scales. Now, whether or not Chern-Simons can be stretched across as a bridge, or whether there's another topological continuum, or a topological continuum of different manifolds, that remains to be seen, but I think the perspective is valid. Now, aside from the passive interactions between informationally persistent macroscale and microscale invariants, there's also a key insight regarding agentic participation in invariant leveraging that we could explore. You can think of an agentic negentropic temporal informational bridge between the micro and macro states. And that has implications because agents are active, they're not passive in the state space. And so let's define some of these terms and consider them. Now we talked about agentic negentropic temporal information bridge. So for agentic, we're just saying that biological or cybernetic agency, the coupled system actively maintains its structure through feedback across scales. Agents do that, biological agents do, and we'd like to say that cybernetic agency could. And so agentic negentropic agents, they actively resist the natural trend towards disorder, and they preserve certain structural invariants over time. So agents actively preserve these maybe more advanced invariants. And then, agentic negentropic temporal information bridge, temporal. In agentic systems, the persistence is not always momentary. This persistence can extend across significant durations despite significant perturbations. So that's interesting. And then the information bridge component here, we're saying that these preserved invariants, they can act as like a shared quote-unquote code. These invariants can act as a code between the quantum micro and the classical macro realms. And finally, again, between the micro and macro states, we're saying that invariants in quantum gauge systems and invariants in the global classical topologies, these can be linked in a way that lets stability on one scale reinforce stability on the other scale. So just in short, agency, as we're defining it, we're defining it stipulatively, I know, but it's a self-stabilizing, time-persistent conservation of information that can transcend scale boundaries. And it can actually link quantum and classical order through shared topological invariants. Think like the double slit experiment, think Schrodinger's cat. There is a transition between the quantum and the classical order that agency itself can ride on or straddle. First of all, then, let's take 2 points. First of all, in the core picture of the argument, we are arguing that persistent information, the stuff about a system that doesn't change under allowed transformations, that this persistent information exists both in the quantum world and in the macro world, and that sometimes these persistent structures are shared across scales. Now, in textbooks, it's said that the quantum scale moves the quantum scale to the persistent invariants. They show up as Chern numbers, Berry phases, winding numbers, and these are protected by quantum symmetries, U and SU symmetries. Okay, but at the macro scale, it goes to persistent invariants that are large-scale geometric topological features. They're magnetic knobs in plasma and crystal lattices. So our point is that in reality, these are not in their manifestations throughout nature as separate as they are expressed in the literature. Nature actually creates these coupled systems where persistence at the macro level informs or constrains the micro level and vice versa. And this means that the same kind of conserved information, it's the same logic of invariance, it operates across scales. The second thing we can say is that number 2 is we're hoping that Chern-Simons is part of this bridge. Chern-Simons theory is normally filed under quantum gauge field math, but topology itself is scale agnostic. And again, we're not sure if we can use Chern-Simon all the way across the bridge, but to me it's useful because of it's not theory. It's chord and not theory. But anyway, if the math describes a persistent structure in quantum field, the math can also describe a persistent structure in the macro field, as long as the topology is real in both domains and the system couples them. So there may be some example bridges here that we can just pick out 3 of them. Like, first of all, the sun's plasma loops. These are magnetic topology at macro scale, and it constrains the micromotions of the charged particles. What about topological insulators? Bulk topology forces surface electrons into protected quantum states. And then, of course, you've got your quantum Hall effect, where this is it's basically magnetic topology plus electron correlations. They're going to produce this invariant flow patterns that resist disorder. And here's the depth of the agentic insight, though. In macro states, we have a largely entropic trend, but the order emerges through invariance in pools around angular momentum. And, of course, at other Noetherian conservation principles as well, not just angular momentum, you've got these invariants, these equivariants, and these symmetries in the environment. And these features themselves are the bedrock negentropic features that persist in the macro state, around which further passive or agentic negentropic accretions can coalesce and crystallize. But the difference between passive negentropic accretion around like galactic or solar rotational disks, for example, and agentic negentropic accretion that we see in agents like mitochondria or paramecium or mammals, the activities of living agents, that difference can be seen in the velocity of and the scale of negentropy accretion, and in the temporal manifestations like invariant special agentic negentropic beliefs and equivariant special agentic negentropic purposes or goals that that emerge in, and they manifest themselves across the operational agentic present, this negotropic nexus. And they manifest themselves through feedback between future anticipatory potential and the past non-Markovian sort of degrading long-tailed memory kernels. In an agentic processing of information, symmetries, invariants, equivariants, conserved quantities, etc., these are like free information that's ambient in the environment for that agent. Right? These persistent features, they could provide either free rides to the agent or they could be obstacles to the agent, and the agent can choose to use some of its energy budget, its metabolically temporal energy budget, in order to break a symmetry or not, depending on the amortization principles that are weighing the current cost versus the long-term savings that would be involved. Our point here is that agency, particularly due to information and energy activities in the operational present, here sandwiched between the informative past and the informative future, that agency also being further informed by sensory data from the environment, which is streaming through as it streams through time, that agency is also busy converting these future potentials into actual past through this negotropic nexus. But here's the key point, that agency can also be accessing invariant information from both the macro, Noetherian, and the quantum, like Chern-Simons and Berry states, for use in this agentic potentiality conversion process. So symmetries are just another information category that feed agentic operational processes. Whether that information comes from low dimension or high dimension states, agency doesn't care. It uses both, and you can see that in nature. We can point out some examples, but first of all, to our larger point about the reductive nature of human thinking and all of these silos that are natural and physical sciences, the connection between the quantum and the macro states are all around us, whether or not the literature acknowledges them. I would even say that humans, we have a awareness sphere and scale. We have a cadence, like an awareness rate, and that we can truncate that rate by reduction. Like we can take our observable sphere and we can break it into parts and reduce it and describe it in pieces. And our ability to do that can be practiced, and it can get better, and that is what we mostly practice, is breaking things apart and describing things in isolation. That's what we practice. That's the skill that we practice. And I would even point to Heidegger, his concern, we're losing our skill to interpret things, which I would say is accretive. Humans also have the ability to take pieces and put them together and to see and then to interpret. We have that ability, but that ability too can get stronger or weaker. It can atrophy depending on whether we lose it or not. And if societally we put so much attention to the decomposition, we get better and better at decomposition and reduction, but we may be getting weaker and weaker at production. These connections between the quantum and macro states, they might be abstracted, they might be hidden by brokered intermediary processes, but they do shine through all around us. So consider the cycles that are involved in plants when they are converting electromagnetic radiation into chemical energy and biomass. And then, of course, we then eat those and we convert them back into electrochemical internal processes. And this is quantum macro collaboration in our nervous systems, in our cellular processes, for example, whereby we then provide waste mass fertilizer for plants who use quantum tunneling for energy harvesting from solar radiation. Again, it's a cyclical process. So agency, like plants and mammals, these are both agents by our stipulated definition. Agency is bridging the quantum and macro states in a deliberate temporal process, whereas passive quantum macro bridges are apparent in non-agentic high energy phenomena in the temporal insulators and etc., as we described above. So, in both the micro and macro states, agency is non-passive in that it uses invariance as information, and this information is scaffolding for agency. It can be that free rider advantage. And agency can navigate both the quantum and macro states to convert potential into actual in cross-spectrum interplay. So in this way, agency is like a mediating abstraction layer that brokers sophisticated collaborative synergy between invariance in the macro state and invariance in the quantum state through purposeful information encoded in either state. And by using this cross-domain information in coordinated ways, consider the flashing of a firefly population, for example, or the deliberate bridging between quantum and macro states, or the capabilities of an electric eel. And it may be conscious, it may not be conscious, but the deliberateness of agency in bridging these states is apparent. So now we're making a case that what's been traditionally treated as two disconnected domains, the macro classical invariance versus the micro quantum invariance, are in fact continuously coupled in real systems, and that the mathematical logic of persistence is the same at both scales. And so this way, then, we have positioned it as essentially, I can just make a claim in 4 points. Point number 1, scale-agnostic invariance. Topological, group-theoretic, symmetry-driven constraints, they exist independent of whether we're talking about Hall stage edge channel or knotted solar plasma loop. The math doesn't care about the units. So again, scale-agnostic invariance. Number 2, physical coupling. Many physical systems are not only purely quantum, and they're not only purely classical, right? In any operational sense anyway. The constraints propagate across domains. We see that. The third point is an agentic bridge, because in agentic systems, whether they're biological, hopefully cybernetic, in agentic systems, feedback loops can purposely, in a specific agentic sense anyway, can purposefully exploit these invariants to maintain order, to maintain negentropy over time. And we can even choose to expend effort to break or preserve symmetries depending on cost and benefit over temporal horizons. So it's a purposeful agentic bridge. Now, is there a passive bridge? That's our fourth point. Because in non-agentic physical contexts, like stellar fusion, like topological insulators, like cyclotron plasmas, the coupling is still there, but without the intentional control. But the same invariants do persist. You see what I mean? So what's interesting in this framing is that we are pushing past this Chern-Simons as purely quantum gauge theory into Chern-Simons as a member of a wider scale-agnostic toolkit. It manifolds in topology. It's just a wider scale-agnostic toolkit to describe persistent information structures, which means that, first of all, macro groups like SO and SE and microgroups like U and SU, they differ in domain, but they share the invariant logic. Here's the logic. Allowed transformations don't touch certain descriptors of the state. It's persistent state, right? Secondly, structures like Berry curvature, like winding number, like Z sub 2 invariance, these are not fundamentally different in kind from magnetic linkage or in kind from angular momentum conservation at astronomical scale. All they are is they're just being just expressed in different degrees of freedom. And finally, where the macro field and the micro state are strongly coupled, persistence at one level can influence, it can even stabilize persistence at the other scale. So we're claiming that this is a genuinely fresh contribution in our agentic negentropic temporal information bridge idea. The idea is that adding agency is as an active selector of which invariants to preserve, to discard, or to break will open a path towards a unified framework for, number one, passive physical coupling of invariants across scales like Chern-Simons to macro topology or macro topology to Chern-Simons, and these would be like nature's cross-scale constraint web. And secondly, that active agentic exploration of invariants, like biological to cognitive systems, using the environment structure as compression, scaffold, or free energy reduction strategy. And so we're just saying that in this context, we've developed an interesting framework for agency we call agentic negentropic dynamics,